Translating words into symbols. Level 1. To solve problems using algebra, it is important that you become comfortable translating mathematical phrases written in words and rewriting them using the language of algebra. In other words, we are taking words that have a specific mathematical meaning and translating it by using mathematical symbols such as numbers and variables. Alright, we are going to systematically go through each mathematical operator and learn how to translate specific phrases into mathematical symbols. Let's start with addition. The common phrases that correspond to addition are the words sum, as in the sum of 5 and x, increased, as in a number increased by 5, and more, as in 5 more than a number. Notice that the variable is sometimes explicitly stated, like in the first phrase, where we need to use the variable x. Notice that some phrases don't explicitly tell you what the variable should be assigned to. In this case, you have complete freedom to choose your favorite letter of the alphabet. Typically, we use the letter N, which represents the word number. Alright, let's move along with the opposite of addition, subtraction. The common phrases that are associated with subtraction are the words difference, as in the difference between a number and 5, decreased, as in a number decreased by 5, less, as in 5 less than a number, and minus, as in 5 minus a number. When translating phrases that involve subtraction, many students have a hard time translating phrases with the word less. Many students translate 5 less than a number as 5 minus x, which is completely wrong. The correct way is x minus 5, because it's 5 less than a number. So you take the number and subtract 5. Okay, let's move along to multiplication. The common phrases that are related to multiplication are the words product, as in the product of 5 and a number, times, as in 5 times a number, and words that explicitly state that we are taking a fraction apart of a number, as in 1/5 of a number. Notice that this last expression can be simplified as n over 5. But for the most part, write it as a product, then simplify. This is going to be important when we work on slightly more complicated phrases. Alright, let's transition to our final operator, division. The common phrases that are linked to division are the words quotient, as in the quotient of a number and 5, and the word divided, as in a number divided by 5. Notice that division can be written using a fraction bar or with the traditional division symbol. For the most part, this classical division symbol will be used less and less in your studies of mathematics. Nevertheless, it will pop up every now and then. At times, a phrase can have more than one mathematical operation, such as the phrase 5 less than half of x. Here we have a difference because of the key word less, and we have a multiplication because we are taking a fraction apart of a number. This expression can also be simplified as follows. In the same manner, the phrase half the difference between x and 5 contains a product because the phrase is denoting that we are taking a fraction apart of a number. In this case, the number is the difference between x and 5, or x minus 5. Notice that we use grouping symbols, specifically parentheses, to group the number that is composed by the difference between x and 5. In addition to translating phrases into mathematical expressions, you also need to be able to effectively work with formulas. Formulas are equations that state rules about relationships. A typical formula that you should be familiar with is the formula to find the area of a rectangle. A is equal to L times W, where A is the area, L is the length of the rectangle, and W is the width of the rectangle. In addition, the formula to find the perimeter of a rectangle is expressed as follows: 2 times the length plus 2 times the width. In other words, you add the lengths of all the sides of the rectangle. Another typical equation that is used in algebra is the distance formula. The distance traveled by an object going at a constant rate for a specific time interval is given by the formula d equals rt, where d is the distance, r is the rate of the object, and t is the time interval the object has been traveling. Finally, to find the monetary cost of a certain number of items, we use the formula C equals NP, where N represents the number of items and P represents the price per item. When using formulas, you need to be comfortable with 2 types of answers that formulas tend to generate. One of them are numerical expressions and the other are variable expressions. For example, say that we would like to find the area of a rectangle whose length is 10 feet and width is 5 feet. Then we use the formula to find the area of a rectangle and substitute the value for the length and width using grouping symbols, as follows. Then we evaluate the numerical expression for a final answer of 50 square feet. The other types of answers that can be obtained from formulas are variable expressions. For example, say we take the same problem, the width is still 5 feet, but now the length is equal to x. In this case, we once again substitute each variable in the formula with the corresponding value that we are given. In this case, the width is equal to 5, and the length is equal to x. So our final answer is 5x. This variable expression represents the area of the rectangle with the given measurements. Notice that this expression is written in terms of the variable x. At first, writing the area this way seems a bit confusing and weird, but all it says is that the area of this rectangle is 5 times x. In the same manner, the perimeter of the rectangle with the same measurements is equal to 2 times 5 plus 2x. Simplifying the variable expression gives us a final answer equal to 10 plus 2x. Again, notice that the answer is left in terms of the variable x. This expression represents the perimeter of a rectangle with width of 5 and length equal to x. The reason why we want to leave our answer in terms of the variable is because by doing this we can generate all the areas and perimeters of a rectangle with width 5 and any length that we would like to have. So if I wanted to know the area of a rectangle with width 5 and length of 6, I just take the variable expression 5x and substitute x for 6. And it turns out that it is equal to 30 square feet. In the same manner, if I wanted to know the perimeter, I take the expression 10 plus 2x and substitute x for 6, and I get 22 feet. In algebra, we sometimes don't want to know the exact value, like 30 square feet or 22 feet. We just want to know in general what the perimeter and area would equal to, given a particular width and any length imaginable. So we use a variable to represent the varying nature of the length. Now let's say that you are riding a bike and you traveled h plus c hours at a constant rate of 20 miles per hour. How far did you travel? So since we are riding at a constant speed, we use the distance traveled formula, which is equal to the rate times the time, and substitute each expression accordingly. Doing that, we have that the distance traveled is equal to 20 times the quantity h plus c, and this is our final answer. Remember, all we want is a general expression for the distance traveled in terms of the given variables. We don't care about specific numbers, just a general algebraic expression for the distance. Okay, let's do one more example using the cost formula. Say that you decided to buy 3 hamburgers, and each one costs $P. What is the total cost of your purchase? So to find the cost, we take the number of items, in this case 3, and multiply it by the price per item, which is equal to P. So the final answer is 3P. Notice that we don't actually have a monetary value. We have a generalized variable expression. But if we knew what P was, then we can find out what the total cost would be. All we need to do is to take the price and multiply it by 3. It is important that you start developing this skill to think algebraically and generalize phrases in terms of variables. Even if you don't know what the particular variable is equal to, we really don't care, unless the problem is asking us to evaluate the variable with a particular value in mind. Okay, in our next video we will go over even more examples and practice translating words into symbols. Translating words into symbols, Level 2. Alright, we're going to work on various examples. It is very important that you understand how to translate phrases into variable expressions. This is the first step in solving more complicated word problems that you will encounter in your studies of algebra and other related science classes, such as physics and chemistry. Alright, let's try the following examples. Translate each phrase into a variable expression. Our first phrase is 10 more than a number. This phrase is describing an addition between two numbers because of the key word more. So this phrase translates to 10 plus n, or n plus 10. Either form represents the same translation of the phrase. Let's try this one. 5 times a number. This phrase is describing a product because of the key word times. This phrase translates to 5 times n, or 5n. Let's try the next one. A number decreased by 11. This phrase represents a subtraction between two numbers because of the key word decreased. So this phrase translates to n minus 11. Many students have a hard time with phrases that involve subtraction because they are not sure which numbers are being subtracted from each other. For example, the variable expression 11 minus n is read 11 decreased by a number. These two expressions are completely different because for the most part, they yield different results when you substitute the variable n with a random number. So be extra careful when translating phrases involving subtraction. Make sure you're subtracting the numbers in the correct order. Alright, let's try the next one. The difference between a number and 2. Once again, we have a subtraction because of the key word difference. So this phrase translates to n minus 2. Alright, let's go to the next phrase. The quotient of 15 and d. Here we have a division because of the key word quotient. This quotient involves the numbers 15 and the variable d. So the phrase translates to 15 divided by d, or 15 over d. Both answers are acceptable, but once again, we usually want the answer with the fraction bar. Let's try a slightly more complicated one. 6 more than twice y. This phrase has two key words, more, which means addition, and twice, which means multiplication. So it's 6 more than 2y, or 2y plus 6. Notice that when we are dealing with addition, the order in which the numbers are added is not important. A word of caution, this is not the case for subtraction. So be careful with phrases involving the subtraction operator. The order in which the numbers are being subtracted matters. Let's try the next example. 10 times the sum of a number and 8. Here we have a multiplication because of the word times, and we have an addition because of the word sum. Also, notice that the product involves the number 10 and the sum of a number and 8. We are going to need grouping symbols for this one. So the phrase translates to 10 times the quantity n plus 8. Whenever you have multiplication, it's always between two numbers. In this case, one number is 10 and the other was the sum of a number and 8. So we need to use grouping symbols to group the expression formed by the sum, which is then multiplied by 10. Alright, let's try the next one. The difference between 3 times a number and 1. So here we have a subtraction because of the key word difference. The two expressions that are being subtracted are 3n and 1. So the final answer is 3n minus 1. Let's try the following phrase. Twice a number increased by 3. Here we have a sum because of the key word increase. So this phrase translates to 2n plus 3, or 3 plus 2n. Whenever you have phrases such as twice, tripled, half, a third, these phrases denote a multiplication. Alright, so now let's go over examples that involve translating phrases that are slightly more practical. Answer the following with a variable expression. Bob is 2 feet taller than Joe. If Joe's height is j feet, how tall is Bob? It's important to read the question as many times as it takes you to understand it completely. The question is describing the heights of Bob and Joe. The question is asking how tall Bob is, given the fact that Bob is 2 feet taller than Joe. We are also told that Joe's height is represented by the variable j. So Bob's height is equal to Joe's height plus 2, or written algebraically, j plus 2 feet. And this is our final answer. Let's try the next one. Maria is 10 inches shorter than Claudia. If Claudia's height is c inches, how tall is Maria? Once again, reread the problem over and over until you understand it. The question is asking how tall Maria is, given the fact that Maria is 10 inches shorter than Claudia, whose height is represented by the variable c. So since Maria is 10 inches shorter than Claudia, we take Claudia's height c and subtract 10 from that. This results in a final expression c minus 10 inches, which represents Maria's height. Let's try a slightly more challenging one. Sam is 3 feet taller than Dan. If Dan's height is d feet, how tall is Sam? Also, if Sam's height is s feet, how tall is Dan? Let's answer the first question. We know that Sam is taller than Dan by 3 feet. We also know that Dan's height is d feet. So to find Sam's height, we take Dan's height and add 3. This results in a final expression of d plus 3 feet. Notice that this expression is from the reference point of Sam. Imagine that you are Sam, and you glance at Dan. You see that you are taller than Dan. So this expression makes sense. The second question tells us that Sam's height is s feet. It is asking us how tall is Dan. So if you were Dan and look at Sam, you would notice that you were shorter than Sam. So your height will be equal to Sam's height minus 3. This results in a final expression of s minus 3 feet. The first variable expression we obtain is from the reference point of Sam, and the second variable expression is from the reference point of Dan. Both contain the same constraint, the fact that Sam is 3 feet taller than Dan. The variable expressions are different depending on whose point of view we focus on. At times, it's useful to put yourself on the character's shoes and think about their perspective relative to the other. Alright, let's work on questions that require the use of formulas. Answer the following with a variable expression. Matthew drove for h plus 6 hours at a constant rate of r plus 5 miles per hour. How far did he go? This problem is a typical distance equals rate times time problem. So we use the distance traveled formula at a constant rate. D equals RT. In this problem, the rate is equal to the quantity r plus 5. So we use grouping symbols and substitute this expression for r on our formula. And in the same manner, the time interval traveled is equal to the quantity h plus 6. So we substitute this expression using grouping symbols for the variable t. Our final variable expression is equal to the quantity r plus 5 times the quantity h plus 6 miles. Alright, let's try the next one. Pencils cost W cents each, and notebooks cost N cents each. How much will 3 pencils and 2 notebooks cost? This problem is an application of the cost formula, C equals N times P. But first notice that we have 2 distinct items, in this case, pencils and notebooks. So to find the total cost, we need to add the total cost of the pencils and the total cost of the notebooks. The total cost of the pencils is equal to 3W, and the total cost of the notebooks is equal to 2N. So the total cost is equal to 3W plus 2N cents. This expression represents the total cost of 3 pencils and 2 notebooks. Notice that the formula we used was a slightly modified version of the cost formula, because of the fact that we had 2 different types of items, in this case pencils and notebooks. Make sure that you understand the problem before you blindly use a formula. Alright, let's work on the final example. A rectangle has a length 5r yards and width of 2s yards. What is the perimeter and the area of the rectangle? To find the perimeter of the rectangle, we use the formula P equals 2L plus 2W, or just add all the sides of the rectangle. So using the formula and simplifying the expression, we have that the perimeter is equal to 10r plus 4s. In the same manner, the area of the rectangle can be found by using the formula length times width. So substituting the expressions into the formula and simplifying, we have that the final variable expression for the area of the rectangle is equal to 10 times r times s, or 10rs squared yards. And that's our final answer. Alright, it's important that you develop this important skill of translating phrases into variable expressions and start thinking algebraically by working solely with variable expressions as opposed to numerical expressions. Okay, in our next video we will expand on this skill of translating phrases into variable expressions by taking sentences and translating them into equations.